So this one is pointing away, like that, meaning that the magnetic field will be going in that direction there, anti-clockwise. Now, in case you remember about the solenoid, this is our solenoid. I can do my solenoid here. I have the wires coming like this, the coils coming like that. And if the current is moving like this in this direction, the current in that solenoid, in those coils there, we say that we use the right-hand rule. Okay? So meaning that if we use the right-hand rule, then the magnetic field will be going in this direction, meaning that yours will be having the north pole. Okay? Which hand are you using? Oh. It is the right-hand grip rule. So if the current is flowing in this conductor here, then the north is in this direction, then the south is in this direction like this. Now, this is what Lenz is all about. It's about the interaction of the field, the magnetic field, of this induced magnetism in this solenoid, and then in the bar magnet. How do they relate to each other? That is what we'll be looking at in Lenz's law. We can continue with our video.
Now, when you say this here, when you say this is for the right hand group,
yes.
The north is right, doesn't say
yes,
down.
Yes.
Now, I think I do like this. No, sorry. If it's facing this side,
if it's facing the other side,
if the current is like flowing.
So if it is facing the other side, then it will be like this. It will be like this.
Like normally, yeah.
Let me draw for you and you see. So if the current is coming from this side, from this side like this, you can see it is passing behind. Let me first finish this. It is passing behind, meaning that this will be going like this. That's the direction of the current. Now, I try to use the directional rule. We'll find out that the thumb is pointing in the other direction. So this will be our north, and then this will be our south.
Okay, now, basically what I'm saying, what I'm trying to ask is, what if they include something, but then the switch, like the way it is there, the current is flowing,
yes,
but then the same.
So if it means that the direction of the current has to change.
Oh, so if the direction is same as the current.
Yes, it changes. So apart from this, we're saying that Lenz is about the permanent magnet and then the induced magnet in the coil. How do they relate with each other? One thing is this. Maybe Janavi can remind us. What is the best law of magnetism? Yes, Janavi?
Unlike poles attract each other, unlike poles repel
each other. Very good. Unlike poles attract, and then the like poles repel each other. That is a very good statement there. Now, what does that tell us? It tells us this. Listen to this, members. It tells us this, that when you have the north and the north, what happens? They repel each other. And when you have the south and the south, they also repel each other. But when you have the north and the south, they are going to attract each other. Now, this is what we're going to be looking at under Lenz's law. Whatever we have discussed is what is going to be happening in this law here. Let's first watch and we see.
When it is placed in a magnetic field which is changing. As the magnet moves towards the solenoid, this induces current in the solenoid. The induced current creates a magnetic field. The loop produces a north pole to oppose the magnetic field of the approaching north pole of the magnet. When the magnet stops moving, there is no changing magnetic field. The current in the loop is zero. Now, when the magnet is pulled away from the solenoid, there is a changing magnetic field in the loops of the solenoid. This induces current in the loop. However, this time the loop has a south pole generated, which attracts the magnet and opposes the motion of the magnet away from the solenoid. The induced current is there.
So, when the current is flowing from the solenoid, it creates a magnet of its own.
Yes.
So wait.
That's where I have begun from. We said that if the magnet is being brought into this coil here, first of all, it induces the current. Like we tried out last time. Like we did last time, and you saw the pointer moving. So if the magnet is coming into the coil, there's going to be an induced current in the coil or in the solenoid, okay? But remember that whenever there is current flowing in the solenoid, there is induced magnetism. Okay? So, in other words, we're looking at a permanent magnet and then the induced magnet in the solenoid. Those two magnets. Yes, Krista.
I got confused.
Mm-hmm.
At first, they were like, when it's coming, that it wasn't the sound.
Mm-hmm.
Yeah. You can't see the sound.
Yeah, they are showing. But the other side, so when they brought it, they started blowing the current.
Have we now got it?
Yeah.
Okay, let's play it again and we see.
Lenz's law helps us to find the direction of the induced current in a loop when it is placed in a magnetic field which is changing. As the magnet moves towards the solenoid, this induces current in the solenoid. The induced current creates a magnetic field. The loop produces a north pole to oppose the magnetic field of the approaching north pole of the magnet. When the magnet stops moving, there is no changing magnetic field. The current in the loop is zero.
And that is also a question that can be asked to you. Like we discussed last time in the demonstration that we had there. That what do you think happened is to the galvanic reading or to the bulb when the bulb magnet has stopped moving in the coil? It stops lighting, like we discussed. So it's something that we are seeing here. Neutral, what do you mean by neutral? Neutral is not a better word. It says that the pointer points at zero, or it doesn't give any reading. And you can even look at this pointer here. It is going right and left, right and left. What is causing that? It's because of the direction of the magnet.
When the magnet stops moving, there is no changing magnetic field. The current in the loop is zero. Now, when the magnet is pulled away from the solenoid, there is a changing magnetic field in the loops of the solenoid. This induces current in the loop. However, this time, the loop has a south pole generated, which attracts the magnet and opposes the motion of the magnet away from the solenoid. The induced current is therefore in the opposite direction.
Okay.
This is a copper gasket. Copper is very conducting, and it's a paramagnetic material, so essentially it's
So you
non-magnetic.
can
So
also
this
carry out
magnet
that
has
here.
no
But I'm
effect
saying
on the
that's
copper
just what it
gasket.
is.
And this is a rather strong magnet, and I can illustrate that with this D-cell battery, which is several times heavier than the copper, but it's easily picked up by this magnet. So now what I'm going to do is I'm going to take this magnet and move it towards and away from the copper gasket. And what you'll see is the copper gasket starts swinging. Now, on the left is another identical copper gasket, except with a hacksaw, a cut has been made through. And as I move the magnet in and out of the copper gasket on the left, you see there's no effect.
What do you think causes that? In this one here, we are still looking at Lenz's law.
See when
No. Yes, let's listen crystal, yes?
like, okay, so this one,
Mhm.
it's like like full cycle, which means that the current, but like it's moving.
The current moves in the whole circuit.
Yes.
And then-
Here, it doesn't like, I think the current.
Yes. So here there is something like the switch is off.
Yeah.
So the current is not flowing in this coil. Yes? Yes, you can also say electrons. Because current means that electrons are flowing.
You said that.
But he's saying that instead of using the current, can you use electrons? And I'm saying yes. Because how we define current? Current means that charges are flowing.
It's away from the copper gasket. And what you'll see is the copper gasket starts swinging. Now, on the left is another identical copper gasket, except with a hacksaw, a cut has been made through. And as I move the magnet in and out of the copper gasket on the left, you see there's no effect. This effect is due to electromagnetic induction. Okay, so when the magnet is approaching the copper gasket, we have an increasing magnetic field inside the copper gasket. That is going to induce a current, and the induced current will be such to create a magnetic field to oppose the increasing field, so the copper gasket will get pushed away. When the magnet is being pulled away,
So that is the same thing that you have just observed in the other video. That if you have a coil, like this, and the magnet is coming. Okay? If the magnet is coming, it means that enough coil is going to be induced this other side to oppose the effect of this other magnet. How about if it was a south pole? Still the magnet is coming. It will make it become a south pole. Very good. In other words, when the magnet is coming towards the solenoid, it induces a similar pole. But when the magnet is going away, it induces an opposite pole. So when the magnet is coming, we expect repulsion. And the magnet is going away, we expect what? Attraction. Correct.
the field inside the copper gasket is decreasing, and so there will be a current induced to try to maintain that magnetic field. So as the magnet is pulled away, it will pull the copper gasket towards it. And so that's why this copper gasket starts swinging. Now with the copper gasket that has a cut in it, you can't have a current flow, so you're not going to be setting up a magnetic field in response to the changing magnetic field inside the path that consists of the copper gasket and the gap.
Okay, the assignment that I'm giving you now, a very simple assignment, is to put that in words. In other words, to state Lenz's, just setting Lenz's law. Only one sentence. You can refer to your notes. You can refer to your notes, the course book. State Lenz's law. Only that. Meanwhile, let me put up our paper that I'm going to discuss in the remaining time. Okay, so we have these questions here, which I need you to give me the answers to. I hope that Janab, you can see it very well on the screen.
Yes.
Okay, can you read for us what you see?
Figure 9.1 shows a permanent bar magnet next to a circuit that contains a coil and a galvanometer. Suggest a metal from which the magnet is made.
Okay, yes, so what can you say about that? Suggest a metal from which the magnet is made. Read the question is there. Very good, that is one. Any other? Right. Suggest a material from which the magnet is made. We can think of the steel. In other words, think of any material which brings about permanent magnetism. Iron.
Cobalt.
Yes, Janab, you are saying?
Cobalt.
Cobalt. And nickel. Okay. Yes, check there and see. Then the next question says that the magnet is moved to the left and is at a small distance into the coil. The calorimeter deflects briefly and shows that there is a current in the coil. Roman 1 says that explain why there is a current in the coil. Explain why there is a current in the coil. What brings about that current in the coil?
Maybe change due to magnetic fields.
Okay, that is Janab V, change in the magnetic field. Okay. I remember Chelsea, you had that question when you carried out the experiment. That's what brings about the magnetism. You said that what brings about magnetism? It's the same question here. Explain why there is current in the coil. Motion on. Yana, repeat for us what you said.
Change due to magnetic fields.
Change to the magnetic field. Where exactly?
Around the magnet.
Around the magnet. Okay, I'm not giving full marks on that. Just I had a question. I mean, you had an idea last time in the experiment. You said that when do we attain much brightness in the bulb? What did you say? When the bulb magnet is moving into and out of the coil, the brightness of the bulb changes. At one point it's very bright, at one point it is somehow less bright. If it is the galvanometer at the point and deflects very much,
When the bulb magnet is coming closer, the current is more. And when it's inside the current is less.
So the magnet is moved to the left and inserted a small distance into the coil. The galvanometer deflects briefly and shows there is a current in the coil. Explain why there is a current in the coil. Now, combining what Ivan has told us and Janavi, what brings about the change in what brings about the current in the coil is basically the magnetic field, which is cutting this solenoid, which is cutting that coil there. So the magnetic field should be affecting the coil or the coils, but not the magnet, as Janavi has said. So here can say that due to magnetic field from the magnet cutting, you can use cutting, you can use crossing. This means creating. Cutting or crossing the coil or the solenoid. Or the solenoid. Okay, that is Roman 1. Then Roman 2, as the magnet is moving near to the coil, any Q of the coil behaves as a magnetic pole. State the polarity of Q and explain why it has this polarity. Poles, north, south.
Oh, so when it's coming close, right?
Mm-hmm.
So when it's coming close, of course, it becomes a like force for the magnet to become outward to repel.
Okay. State the polarity on any Q that is north. That is the north. And explain why it has this polarity.
To repel the magnet.
Okay, very good. The two ends repel. The ends repel. Or repels the magnets. The end repels the magnets. And we know that from what Janaba told us, the like poles repel each other. So if there's a repulsion, then that is a sure way of telling that the poles are the same. Then part C suggests two ways in which the deflection of the galvanometer can be reversed. Deflection is the pointer moving. Reverse means changing, going in the opposite direction. Suggest two ways in which the deflection of the galvanometer can be reversed.
Can you?
Last time we were doing the first point negative. So you can, but now say because even when you're removing it, it can give the negative. But when you also putting it, can also give the negative.
I think when you're using it,
State two ways in which the galvanometer may be made to change can be reversed. Number one is by changing, moving the magnet backwards. That is what we observed last time. In that, according to the question, they say that when the magnet is moving towards, okay, the galvanometer pointed in one direction. So they want us to give advice or to tell what can we do to reverse that point of deflection. So if this one was coming into, then it means that simply pull it backwards. That is one way. Any other one? Change the current. How to change the current? There's no source of current here.
Bring it back.
What can you say about this coil? How about moving the coil itself? Yes, in this experiment, you're moving the magnet.
the wire.
Okay, you can also talk about interchanging the terminals of the coils that can be another, or even moving the solenoid itself. Yes, either moving it away.
You hold the magnet.
In this experiment, you're only moving the magnet. Okay? But you can as well move the solenoid to and away from the magnet. To and away from the magnet. And likewise, and that was different. That was different. Okay, so that was about that question there. we're going to stop here. Our time has ended. See you next time on Friday.
This
Yes, please.
I was asking like this.